how does the induction motor really work? Starting from the very basics of rotating magnetic fields through a new lens of powerful animations, we will be going into the depths of understanding the induction motor and answer intriguing questions such as how it starts and how it generates torque at various speeds. Welcome back to Ingenious. Let us start with the basics. Let us take a copper wire carrying a current. This arrangement produces a magnetic field around the conductor. The current is going into the plane of your screen, which is denoted by the cross mark here. This current sets up a magnetic field, which is set up in a clockwise direction around the conductor. Let us add another wire carrying current in the opposite direction, that is, out of this screen towards you. This conductor sets up a magnetic field that is counterclockwise in nature. When these two conductors are brought closer, their fields interact. They generate a resultant magnetic field that looks like that of a magnet. This arrangement of two conductors carrying currents in opposite directions is called a coil. Let us say that the current passing through the coil is 5 amperes, which produces the magnetic field shown. Instead, if we pass -5 amperes, that is, if we reverse the current flow, the magnetic field also reverses. Notice that the magnetic field vector points downwards for +5 amperes. If we vary the magnitude of this current to, say, 3 amperes, the magnetic field vector maintains the direction, but its strength reduces. For +1 ampere, it reduces further. Similar variation is observed for negative currents, the only difference being that the magnetic field vector points up. Suppose a sinusoidally varying current is passed through the coil, the kind that is found in our homes. In that case, it sets up an oscillating magnetic field, as shown here. This is the exciting thing about the coil. It creates a controlled magnetic field whose control lever is the current that one passes through the coil. Let us take the coil carrying a constant current. The field vector generated by this coil is pointing downwards. Now let us add another coil placed orthogonal to the first coil we had. The field vector generated by this coil points towards the right. Coil 1 is trying to orient the magnetic field, pointing down, and coil 2 is trying to point the field towards the right. The resultant of these two fields points towards the southeast, the bottom right corner. So multiple coils placed at an angle with respect to one another can produce magnetic field vectors at an angle. Let us take 3 coils so that they are rotated 120 degrees with respect to each other. The dotted lines here represent the axis of the coil. Each coil generates magnetic field perpendicular to its axis. If we pass equal currents through each coil, the magnetic fields generated by the coils cancel each other out, and the net magnetic field is 0. Let us pass 0 amperes from the red coil, +5 amperes from the blue coil, and -5 amperes from the yellow coil. This creates a resultant magnetic field, shown by the green arrow pointing to the right. If we pass +5 amperes from the red coil, -5 amperes from the yellow coil, and 0 amperes from the blue coil, the resultant magnetic field points towards 60 degrees, as shown. Similarly, you can get the resultant magnetic field pointing towards any of the 6 directions along the dotted lines by changing the currents appropriately through the coils. And when you do that in a particular sequence, you get a rotating magnetic field. The currents passing through the coils are shown with waveforms here. We get a rotating magnetic field if these current waveforms are passed through the coils. Isn't this amazing? By such an easy setup, we have already created a rotating magnet whose position is totally in our control by means of the current we are passing. When we place a magnet in this field, it tries to align itself with the rotating field we created. In doing so, it rotates at the same speed as the speed of the rotating magnetic field we created. As a matter of fact, this is the working principle of BLDC motors used in drones. Notice that the current waveforms are stepped and discontinuous, which makes the rotation of the magnet also stepped and not smooth. Remember how we passed a sinusoidal current through the coil to generate an oscillating field? If we pass a similar sinusoidal current through our earlier arrangement of 3 coils, each coil sets up its own oscillating field. As you can see, these oscillating fields vary in phase with each other, canceling each other out at every instance of time. The net field generated in this case is 0. But if we pass currents through these coils such that the currents are also shifted 120 degrees with respect to each other, the oscillations no longer cancel each other out. In fact, we get a smoothly rotating magnetic field. This rotating magnetic field is shown by the green arrow in this illustration. When we place a magnet in this field, it tries to align itself with the rotating field we created. In doing so, it rotates at the same speed as the speed of the rotating magnetic field we created. The currents passing through the coils, which are separated by 120 degrees from each other, are known as the 3-phase currents. The rotating magnetic field set up by the 3-phase currents is at the heart of how an induction motor or any 3-phase electric motor works. One such 3-phase motor is the permanent magnet synchronous motor, PMSM for short. Here are some terminologies before we go ahead. The stator is a stationary part that houses the 3 coils or the 3-phase windings to generate the rotating magnetic field. The rotor is the rotating part that houses magnets in PMSM motors. One thing to note here is that the speed of the rotor is dependent on how fast the currents vary. In this case, let us say the current completes 50 sinusoidal cycles per second. In other words, the currents have a frequency of 50 Hz. This results in the rotor completing 50 rotations per second, 50 RPS for short. If the frequency of the currents is doubled to 100 cycles per second, the rotor speed also increases to 100 rotations per second, or 100 RPS. This is a very fundamental permanent magnet motor. In real-world applications like electric vehicles, you can see PMSM motors with multiple magnets on the rotor and multiple coils on the stator to achieve higher torque. Looks beautiful, isn't it? We'll explore this one in detail in a future video. Before we go to the induction motor, we will use our understanding of the PMSM motor to understand the concept of torque in electric motors. Let us take a rotor magnet placed in a magnetic field. In this position, it is perfectly aligned with the external magnet. The North Pole faces the South Pole, and the South Pole faces the North. If the rotor magnet is kept at an angle of delta, it is no longer aligned with the external magnetic field. This creates a torque on the rotor magnet, forcing it to align with the external magnet. If we release the magnet, it snaps back into the aligned position because of the torque acting on it. Let us consider 2 cases where the misalignment angle is 45 degrees and 60 degrees, respectively. In the case of 60-degree misalignment, the torque is higher. The higher the angle of misalignment, the higher the torque acting on the rotor magnet to try to pull it back into alignment. Let us take 2 cases where the misalignment angle is the same, but we use a bigger rotor magnet in one case. In the case of the bigger magnet, the torque is higher. The higher the strength of the magnet or magnetic field, the higher the torque acting on the rotor magnet. If you recall, in the PMSM motor, the rotor magnet was perfectly aligned and rotating with the stator magnetic field produced by the coils. The green arrow represents the stator magnetic field, denoted by FFs. The blue arrow represents the rotor magnetic field, denoted by FR. Now, if the rotor field is misaligned from the stator field by an angle delta, this creates a torque on the rotor to align it back, just like we saw in the case of 2 magnets. This torque is given by the equation shown here. This equation essentially tells the same thing we learned from the two magnets experiment. 1. The higher the magnitude of the field, the higher the torque. Secondly, the higher the angle of misalignment, the higher the torque. This equation single-handedly can explain the torque production in nearly all the electric motors in the world. When the rotor magnet is perfectly aligned with the stator magnetic field, the torque produced by the motor is zero. When a load like a fan or a propeller is added to the rotor shaft, it demands torque from the motor. The rotor falls back from the stator field to create a misalignment and supply the necessary torque. Any motor supplying torque will always have the stator and rotor field misaligned to generate that torque. Now, let's go to the induction motor itself. The stator of the induction motor is very similar to that of the PMSM motor, three-phase coils generating a rotating magnetic field. The genius part that sets the induction motor apart is its rotor, which is made with just three-phase shorted coils. There is no active source supplying these coils. We know by now that we need a stator field and a rotor field to generate torque. Where does the rotor field come from if there's no supply to the rotor coils? Let us find out. Let us take a coil, an open coil, which means it cannot carry any current. Let us say that this open coil is placed in a magnetic field. The magnetic field is such that all the flux lines pass through the coil. This means that there is a maximum flux linkage with this coil. If this magnetic field is made horizontal, no flux lines pass through the coil. There is a minimum flux linkage with this coil at this position. As this external field is rotated at a constant speed, the flux linkage through the coil varies sinusoidally. Now, if you take a voltmeter and measure the voltage in this open coil, the needle will deflect continuously as the flux linked with the coil varies. This indicates that the coil has some induced voltage when the flux passing through it varies. Ever wondered why an induction motor is named like that? Why is the word induction important? This is because the induction motor works according to the law of electromagnetic induction. Because of this law, we see the voltmeter needle deflecting as the flux in the coil is varied. This law allows us to determine this voltage by using this simple relation. Voltage is the negative derivative of the flux linked with the coil. In simpler words, the higher the rate of flux variation, the higher the voltage magnitude. Another way to look at this relation is that the voltage is the negative slope of flux. Consider a point where the flux is maximum. The flux waveform is maxed out at this point, and the slope at this summit point is zero. Thus, the induced voltage is also zero. However, if we consider a point where the flux waveform is zero, the slope of that waveform is maximum, and therefore, the voltage induced is also maximum. This effectively introduces a 90-degree shift between the voltage and flux waveforms. Let us take two more open coils to make it a three-phase coil set subjected to the same external magnetic field. Since these three conductors are placed 120 degrees out of phase with each other, the flux linkage waveforms of these coils are also 120 degrees separated from each other. We can designate red, yellow, and blue colors to these coils and their respective flux linkage waveforms. This is essentially the same arrangement as the one we had seen in the stator of the PMSM motor. The only difference is that the coils are open and cannot carry any current. Applying the law of induction, we can roughly draw the voltage waveforms by shifting the flux waveforms by 90 degrees. This is a three-phase voltage generated by subjecting three-phase coils to a rotating magnetic field. This is how the electricity is generated and transmitted to our homes and industries. We have reached the point where we have now understood that the three-phase coils have three-phase induced voltage in them, but there is still no rotor field. So what's next? Now this is where the genius of Mr. Nikola Tesla comes in. Tesla imagined what would happen if he short-circuited these coils. Once the coils are shorted, the current can flow in these coils because the voltage is already induced in them. Each coil is shorted. Thus, it is a simple RL circuit supplied by a voltage source. For this simple RL circuit, the currents lag the voltage by a certain angle, phi, also known as the power factor angle. Thus, we can easily construct current waveforms for the shorted coils, shifting the voltage waveform by an angle phi. Notice that now, the net phase shift from the stator flux to the rotor current is 90 plus phi. 90 degrees coming from the law of induction and phi coming from the RL circuit of rotor coils. We have just constructed the rotor of the induction motor. Three-phase shorted coils. The currents induced in these shorted coils set up a rotating magnetic field of their own. As we have seen from the waveforms, these currents lag by 90 plus phi to the stator field. Thus, the rotating field vector of the rotor also lags the stator by 90 plus phi. We now have two rotating fields, one generated by the voltage supply given to the stator and another by the induced current in the rotor. Remember, we have seen that torque is generated if two fields are misaligned. This torque acts on the rotor and leads to its rotation. This is how an induction motor starts. Just like the PMSM motor, misaligned stator and rotor fields are causing the torque production here. Remarkable difference in induction motor is the way the rotor field is generated. There is no active source of magnetic field on rotor, no magnets, no supply. Just shorted rotor coils, as simple as it can get. The beauty of induction motor lies in this simple construction of the rotor. Now that the rotor has started rotating, what happens when it catches up with the stator's magnetic field? When the rotor is rotating at the same speed as the stator field, there is no relative motion between the rotor coils and the stator field. In other words, the flux linked through the rotor coils is constant and does not vary at all. If the flux is not varying, there is no induced voltage in the rotor coil and no currents flowing through the rotor coils. Thus, there is no rotor magnetic field and no torque on the rotor. Another way to visualize this better is to see the same picture from the rotor frame of reference. To understand this, let us use the analogy of the Sun-Earth system. If you are viewing the solar system from somewhere outside, you see that the Sun is stationary and the Earth is rotating around the Sun. But if you are standing on Earth, it appears that the Sun and, in fact, all other stars are rotating around the Earth. This is called viewing the universe from the Earth's reference frame. Earth's reference frame gives us an idea of the relative speeds of other objects with respect to Earth. Similarly, if you look at the induction motor from the rotor's frame of reference, you will see a better perspective of the relative motion of the stator field with respect to the rotor. As you can see, in the rotor frame of reference, the rotor is stationary. Also, the stator field does not have any relative motion with respect to the rotor. Thus, no induced current and no torque. This is one of the key characteristics of induction motors. It cannot generate torque at the speed of the stator field. This speed is called synchronous speed. For a stator supplied with a 50 Hz voltage supply, this synchronous speed is 50 rotations per second, 50 RPS. Let's consider rotor speed at 40 RPS. The stator is supplied with a 50 Hz supply, setting the speed of the stator field to 50 RPS. Let's look at the rotor reference frame to understand better. In the stationary frame, the absolute speed of the stator field is 50 RPS, and the absolute speed of the rotor is 40 RPS. When you look at the rotor reference frame, the relative speed of the stator field with respect to the rotor is 50 minus 40. That is 10 RPS. In easier words, the rotor is rotating slower by 10 RPS compared to stator field. So the stator field, linked with the rotor coils, is varying with only 10 RPS speed. So the flux variation seen by the rotor coils is only 10 rotations per second. Thus, the voltages and currents induced due to these flux variations are also varying at 10 RPS. Consequentially, the rotor magnetic field, Fr, will also rotate at 10 RPS with respect to rotor. One important thing to note here, the torque produced is constant only when the two fields are rotating at the exact same speed. If they rotate with different speeds, the angle between them, delta R, is not constant, hence the torque produced is oscillatory. In our case, the stator field is rotating at 50 RPS. To generate constant torque, the rotor field also has to rotate at 50 RPS at all times. For the rotor speed of 40 RPS, we have seen that the rotor field rotates with 10 RPS with respect to the rotor. Thus, the net speed of rotor field comes from the addition of the mechanical speed of the rotor, which is 40 RPS, plus the rotation of rotor field due to induced currents, which is 10 RPS, giving us 50 RPS. Thus, we have rotor field rotating at the same speed as that of the stator field, enabling constant torque production. Let us reduce the rotor speed to 20 RPS. Both the fields still rotate with the same speed. Only difference is that the net speed of rotor field is now coming from 20 RPS mechanical speed of rotor, plus 30 RPS rotation of rotor field. Let us compare 40 RPS rotor speed and 20 RPS rotor speed in rotor frame of reference. If you have a keen eye, you will notice a subtle difference. The rotor field is stronger in the case of 20 RPS rotor speed. This would mean the torque generated is higher for 20 RPS. Why do you think this is happening? From the law of induction, the higher the frequency of variation of flux, the higher the induced voltage. In the 20 RPS case, the flux is varying faster, generating higher induced voltage in rotor, and therefore a stronger magnetic field. Thus, the reduction in rotor speed is resulting in higher torque. Let us quickly look at another famous term used around induction motors. The slip. The slip of the induction motor tells us how far the rotor has slipped away from stator synchronous speed. It is given by this simple equation, as shown here. For the 40 RPS speed, the slip is 0.2. At 20 RPS speed, the motor supplies higher torque, as we have seen earlier. Here the slip is also higher. This is the intuitive meaning of the slip. The more the load on the induction motor, the more the slip in rotor speed away from stator speed. The rotor has to slow down to supply more torque. We have now learned the basic operation of a three-phase induction motor. Our observation so far is that the torque increases as the rotor speed decreases, which translates to a torque speed characteristic that looks like this. However, the typical induction motor torque speed characteristic is the one shown here. The torque does increase as the rotor speed decreases, but after a certain speed, the torque also starts decreasing. Why does this flat topping of torque happen? Based on what you have learned in this video, let me know your theories in the comments. And stay tuned, as I will upload the answer soon in a bonus video. If you like this video, check out other content on the channel. Thank you for tuning in, and see you in the next video.